Hello and welcome to this course of classical mechanics. Now in this course we will be starting from basic Newtonian mechanics and look into different aspects of Newtonian mechanics, starting from standard equations of motion, then work energy, resistance, motion under resistive medium. Slowly we will progress to moving coordinate systems, central orbit, rigid dynamics, and eventually we will go forward into Lagrangian dynamics. So in this entire course it will be a 30 hours lecture, as you might already know, and you must have seen the syllabus. So I will not bother to go into the details of that, but what I will start with is giving you a list of reference books. So the first reference book which I would like to show you is this one. This is the Classical Mechanics by Herbert Goldstein. It's not a very easy, it's not a very easy reading, but it's a wonderful book, and I would request all of you to have one copy of each. Now this one, it's a Theoretical Mechanics by Spiegel, and it is a book which is full of problems. Every simple theories are also described as if these are some small problems, and this is also a very good book, and I would request you also to have one copy of this. Then the other book which I strongly recommend is this short notebook. It's a very thin book which is by a very famous, very well known, reputed eminent professor, Professor Amol Kumar Rai Choudhury, who is a professor in Calcutta University, and it is a collection of his class notes essentially, and this is also a very good book, especially for the advanced topics. And finally there is this book which is Classical Mechanics and General Properties of Matter by S. Maiti and Devi Prasad Roy Choudhury, which is primarily used in certain universities of West Bengal, but there are certain things which will be specially meant, which I will mention specially during the lecture. For example, certain chapters related to rocket motion and all, which will be which you will find nowhere but only in this book. Okay. So as the class progresses, slowly we will see the difficulty level will increase, and at certain times I might refer to one of these 4 books and maybe some other books which is also mentioned in the syllabus, and slowly we will go into the details of the subject. Now let us start with a review of classical mechanics, review of basic Newtonian mechanics, as we can call it. So we all know that the fundamental equation is F equal to ma. So this is the fundamental equation which comes from Newton's second law, as a consequence of Newton's second law, and this is the most fundamental equation of Newtonian mechanics. Now if we break this term, we know that this is nothing but r double dot, which essentially means m d2 r d d2. Now please keep in mind that this equation is valid only for systems with constant mass. So this equation is valid for systems with constant mass. If the mass of the system is also changing, then this equation is not strictly valid, and we will have one additional term which we will see when we will be discussing rocket motion. Okay. Now for now let us assume that the systems which we are considering in this class and next few hours, where the systems are with constant mass, and we have this vector equation, that F equal to m second derivative of the position vector. Okay. Now we can rearrange this equation slightly, and we can write it as m d V dt, where V is equal to dr dt. Okay. And then we can slightly rearrange it once again, and we can write this as dr into dr dt. Okay. Now, if you look at this term here, this is nothing but your V. So, this can be written as mv dv dr. Okay. Now, if we consider motion in one dimension, 1D motion, then your V is nothing but dx dt and r is nothing but x, and this entire equation, vector equation, can be reduced to m v dv dx, okay, which can also be written as f m v dv dx is, sorry, there is no vector sign here. So, this equation is the scalar equivalent of this same equation in one direction, one dimensional motion, when the motion is only along x direction. Now, in this form, this equation, if we compare it with the standard f equal to m dv dt, where v is the velocity along x direction. So, this is simply a rearrangement of this equation here, but this equation in this particular form is very useful, as we will see very soon. Now, let us try to review some fundamentals of classical mechanics, Newtonian mechanics, by using this form. And please keep in mind that we will be using systems with constant mass. So, I will just leave this line here and not remove it. Okay. Now, let us assume that one particle of mass m, which is again a system with constant mass, is moving from point 1 to point 2, and the work done, which is can be written as W12, is, as we all know from the fundamental principles of mechanics, is F dot dr. Okay. Now, once we use the modified form of this force F, we can rearrange this to write F, so essentially we replace F with dr dot dr. Okay. So, this will be nothing but m v dot dv, which is nothing but half m integration 1 to 2 d of v square. Okay. There will be a factor of 2 coming here because of this change in notation. So, it will give us half m v2 square minus v1 square. Okay. Now, if we consider at the same time that this force field F is a conservative force field, then what do we get? Then according to the definition of conservative force field, we know that for any conservative force field, curl of F is equal to 0. I am sure that you are familiar with this particular operator. It is the delta operator, and it is written as del x I cap plus del y j cap plus del z k cap. So, it is essentially a vector operator, and this particular operation is the curl operation, which is a cross product between this operator and this force field F. Now, this will be true if and only if force F can be written as gradient of some scalar field phi. This is the definition of conservative force field, and this equation is valid only if F can be represented as gradient of some potential function phi. This negative sign essentially implies that the force increases in the direction where phi decreases, and this has some other implications which we will be discussing later on, this negative sign. Now, for now, if this is the case, then curl of F is curl of grad of phi, and from our vector calculus we know that curl of grad of something, some scalar field, will always be equal to 0. So, if this is the case, then this will be a valid equation. So, now if we go back to this work done, W12 which will be equal to F dot dr, we can write this as integration or W12 as integration 1 to 2 F dot dr, which will be 1 to 2 minus grad phi dot dr. Now, this dr is any arbitrary displacement, arbitrary small displacement vector in this entire xyz coordinate system. So, dr has this general form of dr equal to dx I cap plus dy j cap plus dz k cap. I will just write it once again, which might not be. So, dr equal to dx I cap plus dy j cap plus dz k cap. Okay. So, this equation, this integration, if we complete this dot product between grad phi and dr, then we will essentially get integration 1 to 2 del phi del x dx plus del phi del y dy plus del phi del z dz, and this whole thing from the fundamentals of differential calculus, this entire term is nothing but integration 1 to 2 d phi. Phi being a function of x and y and z, please remember this phi here is a function of x and y and z. So, d phi is del phi del x dx plus del phi del x dy plus del phi del z dz. So, then this equation, the integration will essentially give us phi 2 minus phi 1. Now, let us compare this two. We do not need this anymore. Now, if we compare these two W12 expressions we have got from both sides, so essentially what we get is half m v2 square minus v1 square equal to phi 2 minus phi 1 and a rearrangement essentially gives half m v1 square plus phi 1 equal to half m v2 square plus phi 2. And this is our familiar expression of conservation of total energy. This part is the kinetic energy, this is the potential energy of the particle at point 1. Similarly, this is the potential energy, kinetic energy of the particle and potential energy of the particle at point 2. So, we see when a system with constant mass is moving in a conservative force field, then the total mechanical energy at point 1 and point 2 remains the same, which is a very well known principle. We just derived it using this slightly different form of the force F. Okay. So, this is one thing I wanted to discuss. Next, we would like to define what is meant by an inertial frame. Now, an inertial frame is a frame of reference in which, or let us define it in this way. We have two inertial frames and we try to construct the equation of motion of a particle moving in a conservative force field or any force field, that is to say, in both the frames. So, we have a frame 1 with coordinate systems, let us say O prime, x prime, y prime, z prime, and let us say this is the particle of our interest, and this particular coordinate system, this particle has a vector position vector as r prime. Assuming there is another coordinate system which is given as O, x, y, z, the same position, same particle has a position vector which is described as r in this particular system. So, we have one frame which is x prime, y prime, z prime, another frame which is x, y, z. We have the position vector of same particle. Please remember, the particle remains the same, but the reference frames are different. So, in one reference frame this is given as r prime, in another reference frame this is given as r, and let us assume, let us say that the origin of these two frames are connected by this vector capital R. So, from the triangular law of vector addition, we can immediately write an equation which is r prime is equal to r plus r. Small r prime is equal to capital R plus small r, which comes from the triangular law of vector addition. Now, if we take time derivative, by the way, time derivative, this operator is equivalent of placing a dot. Let us say if dA dt then is equivalent to saying a dot. Okay. So, if we take time derivative of this equation, we get dt equal to dr dt plus dr dt. Okay. Now, assume that this frame is fixed and this frame is moving. So, this is a frame which is fixed in space and this is a frame which is moving with respect to this frame. So, the velocity of this frame, the movement of this frame is given by, or I will just write it as capital V is equal to r dot, right. Going back to this equation, we can write r prime equal to V plus r dot. Okay. Now, if we take the second derivative, then we have r double dot prime is equal to V dot plus r double dot. Double dot is equivalent to taking two time derivatives. Okay. Now, this equation, if we just remember the fundamental form of Newtonian equation, which is m d2r, or rather m r double dot is equal to f. Okay. Now, if we recall, this is the fundamental form of Newtonian fundamental equation, force equation of Newtonian mechanics. Then, if we have a velocity v which is not a constant, then definitely we have r double prime dot, r prime double dot is not equal to r double dot. But if we have a situation where this velocity is a constant, then we immediately see this term cancels out and we have equal to r. So, that means if this frame, this particular frame is moving with a constant velocity with respect to this frame, then the equation of motion of this particular particle, whether we construct it is construct this equation with reference to this frame or that frame, it will remain invariant, because in the second derivative of the position vector it remains the same. But if the velocity is not a constant, then what we will have is an additional term which is v dot, the velocity dot. Okay. So, this happens if and only if v is a constant. So, by definition, an inertial frame is a frame which is either at rest, like this one, rest as in rest with respect to the rest of the universe. We are assuming that everything is static and we have a frame which is also static with respect to the surrounding, and this is called an inertial frame. Now, if the frame is moving with a constant velocity with respect to a fixed frame, that is also can be called an inertial frame, because as we have already seen, the equation of motions with respect to that particular frame will also be invariant. So far we have learned two things. One is the slightly different form of the Newtonian equation, and from there we have derived the fundamental principle of conservation of energy, conservation of total mechanical energy. And secondly, we have learned what is an inertial frame, and we have seen that the equation of motion of a particle remains invariant in an inertial frame irrespective of the velocity of the frame. If the velocity is a constant, does not matter how fast or how slow it is moving, inertial frame remains an inertial frame. But if the velocity is not constant, then we have something called a non-inertial frame of and then we have to reconstruct the equation of motion. We will be taking that up in a later chapter. Okay. So, what we will do now, we will give you some examples of different types of forces. One is F equal to constant. So, this is called a constant force. constant force field. So, there is no specific example given, but for example, gravitational pull you can assume near to the earth the gravitational acceleration is constant on all the objects. So, that is an example of a constant force. Okay. Then we have F equal to F of t. An example is, let us say F is equal to F0 cos omega t. So, this is a periodic force which changes, the magnitude of the force changes with time. Thirdly, we can have something like F of r. For example, F is equal to r cubed, r by r cubed. So, this is a central force. So, we will have a separate chapter on central forces and we will discuss this force field in a good details. And finally, we can also have a force which is proportional to the velocity. An example of this is the viscous drag force. Okay. So, this is an example of an object. This particular force is the resistive force. For example, if a particle, if I throw this chalk through the air in this room, this will have, instead of, so alongside the gravitational pull, it will also have a force field due to the presence of air in this room. Okay? And that force will be proportional to the velocity of this particular object. So, this is called a viscous drag force. So, all these types of forces will have, so this one will not immediately discuss this type of forces. Constant forces, we will take examples of constant forces in different, for different context. This particular force field, the periodic force, we will keep it for the end. If we have time and we can discuss the details of small oscillation, we will go into that. This one is a central force. As I said, there is a separate chapter dedicated to this type of forces, and this is the viscous drag force which we will be discussing in the very next chapter. Okay. And also there are some other examples, other mathematical examples, but I think that can be done towards the end of this chapter of review of Newtonian mechanics, which we'll have one more classes on, I think 2 more classes on this, and after that we can have a detailed discussion on the examples. Thank you.